Good evening, ma'am.
Good evening. Where are you from?
Ma'am, I am from Patna, Bihar.
Oh, okay. And which university are you in?
Haldia Institute of Technology in West Bengal.
Okay. Actually, that institute is very close to my place.
Yes, ma'am.
I'll just join since it's echoing. So I'll just join again.
मैम आपकी तरफ से बहुत नॉइज आ रहा है.
अभी सही है?
यस मैम.
हम्म. तुम हल्दिया जाते होंगे तो कैसे आते हो हल्दिया?
ये तो आप कैसे ट्राई कर लेता हूँ मैम हल्दिया के लिए.
अच्छा अच्छा. तुम नेचुरा ऐसे क्रॉस करते हो ना?
यस मैम.
हाँ, वहीं पे रहते हैं हम.
ओके. मिश्रा में रहती है मैम.
हाँ, मतलब उधर घर है, अभी तो हैदराबाद में है. हम्म. Okay, in which year you are?
मैम लास्ट ईयर.
Okay. तो ये this course superconductivity how this helps you मतलब कोर्स में है क्या क्या?
सुपर कंडक्टिविटी कंडक्टिविटी में मैंने बहुत कुछ सीखा है मैम. मतलब बहुत कुछ नया भी कुछ पता चला मैम. मतलब इसके बारे में पहले अवेयरनेस नहीं थी. आप तो सब कुछ मैम एक्सेल शीट में भी शेयर कर देती है, तो मैं वो भी देखता हूँ. बीच के मैंने 2 क्लासेस भी नहीं किए थे. तो इट्स वेरी गुड मैम. मतलब इट्स हेल्प्स मी लॉट मैम अबाउट नोइंग द सुपर कंडक्टिविटी फील्ड के बारे में. इज गुड मैम. मतलब गुड एक्सपीरियंस.
अच्छा, like this is not directly included in your coursework or something?
जी.
अच्छा. Okay. So I guess if anybody else joins, they can join later. We can start now.
यस मैम.
Hmm. So yes. Have you received the solution of assignment 4?
हाँ जी मैम.
Okay. Okay, we'll try to solve that one only. And when was the when is the exam?
रूटीन में देख के आपको भी जस्ट बता दे रहा हूँ मैं.
Okay. So we'll start. The first question is they asked us to describe the working principle of a squid. So squid is what? Squid is an instrument which measures magnetic fields. Now, what kind of magnetic fields? Squid is very sensitive, like sensitive towards magnetic fields. So squid can detect like extremely weak magnetic fields as well. So it basically operates based on this superconducting loops containing Josephson junctions. Okay. Hmm. So firstly, I write working principle of squid. First one is this Josephson effect. It operates. Then the next one is the phase difference across these Josephson junctions. This is related to magnetic flux passing through the loop. Okay, I'll just write here. It can detect weak magnetic fields as well. So the second one I was talking about the phase difference across the junction is related to magnetic flux passing through the loop. Now the third one will be as the external magnetic flux changes, the critical current oscillates. Okay, it oscillates due to flux quantization. Critical current, or we can write it IC, oscillates periodically due to flux quantization. And the fourth one will be these oscillations allow like variation in magnetic field. So, what is the answer? Basically, the answer is squid is a magnetometer which can detect extremely weak magnetic fields as well. Now, what is the working principle of squid? It operates it since it is a magnetometer, so it the superconducting loop allows this quantum interference to happen due to the presence of Josephson effect. Now, in this Josephson effect, we know about the Josephson junction and the phase difference between this junction. Here magnetic flux passes. Okay, means yeah, magnetic flux passes through this loop, and when critical current oscillates like due to flux quantization, this allows variation in the magnetic field, and that's how the squid can like detect it, and it shows us the value or whatever. Now the second question is what are its application? What are the applications of squid? So of course, squid like any magnetic thing, the first application should come in your mind is the medical imaging, like MRI. Okay, and but nowadays like other medical equipments have also been invented. So in that for like mostly for that brain activity monitoring, right? We use and like in quantum computing, of course. Then seismology. If you have heard of that, like seismology is basically uh, it includes in geophysics. Yeah. They detects minute magnetic field variations in the earth. Okay, like gravitational waves, etc. So I'll just jot them down. Applications of squid. The first one is medical imaging purpose. The second one is quantum computing. Third one is in geophysics. I'm just writing geophysics. Then show VI characteristics of a squid. X-axis is I and Y-axis is V. Yeah, this is the VI plot for squid. So as the voltage becomes non-zero with the increasing I or current, the critical current IC we get. Okay. Mhm. Basically, critical current you can write it as the maximum supercurrent that flow without voltage appearing across the junctions. So it can be determined by experimental by measuring the maximum current before a voltage drop, right? Before a voltage drop. Now, the how does one determine the critical current? I see, yeah, the same thing. This is a VI plot, and that's how we determine. Before the voltage drop, IC comes. Or you can say that when the voltage becomes non-zero with increasing I, that time only you get the IC value. Then the Oh, this is AB. Okay, fine. For a DC squid, as shown in the figure below, obtain an expression of the total current of circulating in the loop. Express your result in terms of sum and differences of the phases of the wave function phi and uh, अच्छा phi 1 and phi 2. DC squid they have told. Acha, it's drawn already. Okay, I am watching the question paper, so I hope you can also watch if you want. They have asked you to expression for total current and in terms of sum and differences of ion set. Okay. So basically DC is squid, right? So DC is squid, this contains about two Josephson junctions connected in a superconducting loop. So first they have asked us to determine the total current. So total current I we can write as in terms of phi and phi 2, right? Two phases. So E I phi 1 plus I 2 E I phi 2. Now I1 and I2 are the currents through the two Josephson junctions and phi 1 and phi 2 are the phase differences of the this superconducting wave function. Now also if you expand this E term, exponential term, you can write it as like in terms of what's say IC to critical current, you can write it as yeah. Find and the second one is find an expression for phi 1 and minus phi 2 in mod from the phase difference around the loop. So from the phase coherence condition around the superconducting loop, we can write it as phi 1 minus phi 2 equals to 2 pi divided by phi naught phi external plus L I S. Okay, now what is this? So phi 1, phi 2, you know phi, what is the phi term? Now phi external is the externally applied magnetic field. Externally applied magnetic field. And L is the self-inductance. 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 Now, the third question is now compute the total flux. Total flux means only phi. Total flux. Assuming L is to be the self-inductance of the circuit and phi external is phi will magnetic field B, express it in terms of any phase. It's just this one only, the above one. Phi external plus L I. Just this one. I is what? I is this. I is this total circulating current. I'll just write I is total circulating current. Now, they have asked express it in any terms of any of the phases phi 1 and phi 2. Okay. From this term only we have to pick. So, phi external is L. I, yeah, the I, this thing we can write it here in place of I, L into 2IC cos of phi 1 minus phi 2 divided by 2 sine phi 1 plus phi 2 divided by 2. Right. So this is the in terms of phi1 and phi2 we can write. Now the fourth question is, what is the maximum current I max for L equals to 0? From here we can only detect when L equals to 0. This means what? This means that the zero self inductance, right? And when the maximum current occurs, then also phi1 minus phi2 equals to 0 happens. Okay. Then I max will be 2IC cos, means if I take everything from this equation. Okay. So 0 equals to this, right? 0 equals to 2 pi divided by phi 0 phi external plus 0, right? Then I max is what? Then phi external, the value you'll get of phi external. What is this? Okay, that would be 0 only. Now if we put in the I max equation, it will be 2IC cos of pi phi external divided by phi 0. Let me check once. Okay, I got it. So we have to do this one. Like phi in this value, if we put, then only we'll get it. Okay, then the next one is establish a connection with Young's double slit experiment in optics. What is the source of phase difference in this case? Okay, so fifth one is Young connection with Young's double slit experiment. The you know Young's double slit experiment, right? In the from there we get the interference pattern, and it's similar to this interference pattern that we get from the squid. So the phase difference source will be such that in optics, when we do that such kind of experiment, the phase difference arises due to the path different of light waves. But in a squid, the phase difference happens when the magnetic flux, like when goes through the superconducting loop. That's that's one difference. So in I'll just write here young double slit experience, and this is only squid. So here phase difference, if phase difference is the main characteristics, then phase difference appears due to the path difference of the light waves. But in squid this happens due to the magnetic flux through the superconducting loop. Okay. So that's one thing. And then the next question we can go. The next question is, what are the main assumptions of Fermi liquid theory? Describe the conjuncture of adiabatic continuity. Okay, the first we'll do that much only. FLT theory, no? FLT. So basically, this theory, who has introduced this? This is introduced by Lev Landau in 1956. Okay, like to describe the strong interacting systems of electrons in metal. Okay, where the Coulomb interaction is also there. So the main assumptions of FLT will be one. If we write in detail, this we can write it as existence of quasi-particles. So, so what happens in an interacting electron system? The concept of quasi-particles replaces the free electrons. Okay, such as in metals, you see the free electrons are there. Now, a quasi-particle is basically an electron traced with a cloud of interactions from surrounding electrons. Okay, now these quasi-particles have one-to-one correspondence to the free electrons of a non-interacting system. Okay, now this has been normalized by effective mass. Okay, so it is so that comes as in different from the normal bare electron mass. Okay, I'll just write this thing, like this is a story kind of thing, you just have to realize it. That's the thing. Existence of quasi-particles. So quasi-particles present in an interacting electron system, right? And what is it? Quasi-particles? Quasi-particles are electrons dressed with electron with a cloud of interacting of interactions from surrounding electrons. Okay, so quasi-particles are basically uh, an electron surrounded with a cloud of electronic interactions from the neighboring electrons. Okay. Now, the second thing will be adiabatic quantity, continuity. So the ground state of an interacting electron system is continuously connected to that of a free electron system as interactions are turned on. Now this means that the Fermi surface remains well defined even in the presence of any interactions. Okay, so although there is a next question regarding to this, but here just I'll just brief it down. Of an interacting electron system is continuously connected to that of a free electron system. Now, the third point we can write it as a well defined Fermi surface, like which got led by the adiabatic continuity. So, like in a free electron model, this Fermi liquid theory assumes that at zero temperature, all electronic states below the Fermi energy are occupied. Okay, and this like above are all empty. below zero temperature, zero electronic states, electronic, okay, I'll just draw it rather. If let's say this is EF, Fermi energy, then this and this, let's say this is case 1, this is case 2. In case 1, these are all empty, these electronic states, and this one, these are all filled. Okay, this happens only at below zero temperature. Now this occupation number follows a slightly modified Fermi Dirac distribution. That's a different kind of story. So the fourth point will be this lifetime of these quasi particles. So this stability, or in the sense, what do you say? Mm, okay, like let's say the lifetime only. We can write it as tau, right? So it's basically 1 by E minus EF square, right? So the basically what happens if quasi-particle diverges as it approaches the Fermi surface. So that ensures that quasi-particles behave like free electrons only at the low energies. The E is Landau interaction parameter. So this means the interaction between the quasi-particles that are described by a set of Landau parameters. So these parameters are like these parameters describe the properties like specific heat, magnetic susceptibility, electrical resistivity, etc. Okay, describes properties like specific heat, magnetic susceptibility, electrical resistivity, etc. Now describe the conjuncture of adiabatic continuity. So this is one of the most like a crucial concept of this Fermi liquid theory. So it tells that if we start from a free electron system and gradually introduce interactions one by one, then the ground state will continuously evolve without undergoing any abrupt phase transition. What does it mean? That means the Fermi surface remains intact. The low energy excitations the low energy excitations of the interacting system will be similar to the free electron system, and quasi-particles remain valid like excitations. The electron system does not transform into a fundamentally different phase. Okay, so what did I tell? The Fermi surface remains intact. This is basically the summary from what have I told just now. Fermi surface intact. And the second point I told that quasi-particles Okay. Now, what do we like? What is the like? What will you carry forward from this? What will be the physical interpretation? So, physical interpretation is such as that like just these things I have told, no, like this specific heat and all. So, what happens? The specific heat uh, of an electron system remains linear to temperature, like proportional to temperature. Okay, just as in case of a free electron, but with a like there includes an effective mass. Okay, that's how it gets modified a little bit, but it's similar to the like for both the systems, the relation with temperature is similar. Okay, that's the for specific heat. Then for the next property, let's say resistivity. Resistivity obeys Fermi liquid scaling. That is the for like relation with temperature is such as rho is proportional to t square. Okay, with t, as t increases, the root of rho increases. Like root in the sense root over root. Huh. Now the magnetic susceptibility. The magnetic susceptibility is like the same of the free electrons only. Okay. So this is the physical interpretation. Now the next question is, what are the signatures of breakdown of FLT in cuprate? Superconducting. You know that cuprates are the cuprates are the superconductors which does not like obey the BCS theory, where the quasi-particles are not well defined. Now the resistivity is same, just as I told. No, sorry, resistivity is not same. Specific it is same. But CP is proportional to T, right? CP is proportional to T, but I told rho is proportional to T square. This is for this FLT, Fermi liquid theory. But for cuprates, it is the rho is proportional to T only. And this is due to this superconducting mechanism is different, right? So it happens due to the electron correlation driven. Okay, but for FLT, it's phonon mediated. Now, for magnetic susceptibility, what did I tell about this FLT? It behaves like that of free electron, right? But for what's a cuprate, it varies strongly with temperature, whereas for the FLT, it's weakly dependent, like not that much dependent, but okay. And these cupric superconductors are like discovered long ago, like 1980s. It does not follow this Fermi liquid behavior. Instead, they exhibit non-Fermi liquid properties, right? Since the opposite, this terminology has been given. Now, especially in the normal state, that is above the TC, above the superconducting critical temperature. Now, what are the observations they have in the question they have asked us? So, the breakdown of Fermi liquid theory in cuprates is seen through several experiments, right? So, the first one is metal phase like linear resistivity. Okay, just write dependence on rho. Dependence of rho. So, I just told you here in FLT it follows this rho proportional to T square, but here its rho is proportional to T, right? So this is also called, and this temperature, this phenomena has been observed with a wide range of T, means like let's say a greater gap in the maximum and minimum temperature, and this range is also named as strange metal phase. Okay, now the first one is this. Now the second point will be Absence of well-defined quasi-particles. So you already have told that in FLT, quasi-particles have long time, long lifetimes at low energies, such as here only I can write tau is proportional to tau. I have written someone, yeah, that here only I have written. Yeah. So this is long lifetimes, but in cuprates, this formula is not obeyed. This equation is not obeyed. Okay, so it behaves such as tau is proportional to 1 by t. Okay, this suggests that strong inelastic scattering that disrupts the quasi-particle coherence. Okay, now the third one is pseudo gap phase. So pseudo gap is basically an energy gap only that opens up in the density of states DOS, even the superconductivity not got set in, like not get sets in, but still pseudo gap will be like you will see. No, now unlike a Fermi liquid, which follows a FLT, but there the density of states remain constant near the Fermi level. Like cuprates exhibit a separation of states due to the pseudo gap. Just say. So unlike a Fermi liquid, where the density of states are there in the Fermi level, for cuprates there is an exhibition of separation of states due to this pseudo gap. So this, what does this do? This suppresses the states near Fermi level. Now, this phase is highly anomalous and incompatible with the Fermi liquid framework. So that's how it stands out. Now, the fourth one will be unconventional superconductivity. That's I told in the beginning only of this question that it does not obey the Messier theory, right? Like in the Fermi liquid, superconductivity is usually mediated by phonons, but here, in the cuprates, the pairing mechanism happens. Okay, like strong electron correlation, like strong electron correlation takes place, and that leads to superconductivity. Now this superconducting order parameter, if you remember, has an unconventional d-wave symmetry, differing from this s-wave pairing in FLT or any conventional superconductors. So unconventional superconductivity, what does it tell? Normally we see S wave, right? But here it is D wave symmetry. It follows. Okay. This one is non-standard magnetic susceptibility. Or I can just. Okay. So in FLT, I have already told that this is weakly dependent, but here it is strongly dependent. Yeah, this things only will be there. Now, these are the signatures of breakdown of FLT in cuprate superconductors. Now, the third question is Write down Josephson equations. Write down Josephson equations for current and voltage across a tunnel junction between two superconductors. Explain AC and DC Josephson effects. Compute the wave function and hence the current inside and where with it. Okay. So Josephson junctions are quantum mechanical devices made of two superconductors separated by a thin insulating layer. Now, this they exhibit remarkable quantum interference effects. Okay, that leads to supercurrents without any applied voltage, and AC oscillations when a voltage is applied. Okay, now the first thing we have to write is the Josephson equations for current and voltage. So first, so current phase relation will be I equals to IC sine phi, where I is the supercurrent. I is the supercurrent and this is critical current. Now, this is the maximum current the junction can carry before breaking superconductivity, and phi is the phase difference, you know already. Now, this is the current relation. Now, voltage relation, voltage phase relation, what will be? It is equals to V equals to equal d phi by dt. Now V is the voltage across the junction. This this is the reduced Planck's constant, and this one already electrical charge. And this equation shows us that the how time varies with the phase difference, leading to a voltage ultimately. Now the second question is, explain AC and DC Josephson effects. Now first we'll do the DC one. DC Josephson effect. So if no voltage is applied, when V equals to 0, the phase difference is constant, right? And the current across the junction will be given by I equals to IC sine phi. This means that a constant supercurrent flows without any resistance, right? Which is the basis of superconducting currents. That's the thing only. Now AC Josephson effect, it tells that when a constant voltage is applied across the junction, the phase difference, we can write it as for time, right? And if we substitute this into this formula, then we can write it as IC sine, not phi t only we are replacing, no? So phi naught plus 2 EV by H naught T. That's the thing, yeah. Now this shows that the current oscillates at a certain frequency, and this we can also write it as Fj. So this is a very like this is used to like precise voltage standards. Okay. Now the next question, compute the wave function. And hence the current inside a tunnel barrier of it, and this. I think this answer will be like this only what I'm thinking. Okay, the wave function inside the insulating barrier, here width is A, it's given. It follows the Schrodinger equation, right? So we can just write that x square minus 2m h square v naught minus E phi equals to 0. Right. So this is general solution of the exponentially decaying any function like phi x. We can write as a to the power minus kx plus b to the power plus kx, where k equals to root 2m v naught minus e divided by h. This is a decay constant, right? So if we apply the boundary conditions where x equals to plus minus a by 2, right? So the Josephson current is derived, then we can derive in the terms of phi 1 and phi 2, where we already know I c equals to sine phi 1 minus phi 2. Okay. Now the fourth question is, draw the screening current Is as a function of the applied magnetic flux phi and so explain the variation. Now, you already know that squid. What is a squid? So it's it's a magnetometer to detect extremely weak magnetic fields, and this device has two Josephson junctions in a loop. Right. Now, screening current is the circulating current in the squid loop that opposes the external flux, and it follows the an oscillatory behavior. Just previously also we have done that, which is Is equals to Ic. That time I have wrote only I, but it's Is also you can write cos phi divided by phi 0. Now phi is the applied magnetic flux, and this one is a magnetic flux quantum. This can also be write as also as this magnetic flux quantum. So we can draw like this. So the max, this is IC. So the yeah, sorry, 2IC, and the y-axis you can write it as I max. So the maximum is 2IC when this equals to n phi 0. N is any integer, and minimum will be 0 for, then this will be n plus half is 0. So yeah, that's the thing. And then the write down the this is Spotna. So explain the variation. Yeah, thanks. Now present in a schematic plot. This is the schematic plot only. The output voltage, the function of the applied, that is 550. This I have done somewhere. Okay, also we can write again. No problem. So, output voltage versus magnetic flux, right? Uh, So, the voltage output of a DC squid, it is written such as the same thing for current and for voltage, right? Now, V naught is the peak voltage. Now, this is the same thing, same diagram will be there, and the voltage oscillates periodically here. So, this is the basically the basis of these ultra sensitive magnetometers like squid and all. Now, the fifth one, I'm not just drawing the same thing even. Now, describe a Josephson junction. So, as we have already been told many a times, these Josephson junctions are the fundamental of the superconducting circuits. Any quantum computing or the precise measurements of this magnetic fields. Now, they have asked us write down the expression for current and voltage in terms of the phase phi of the condensate wave function. Okay. So, I equals to IC sine phi. The questions are repetitive only, and this is the current equation, and the voltage equation is this. See, where we have done this only. Describe the AC and DC Josephson effects. So DC Josephson effects appear when V equals to 0. A constant supercurrent flows. Uh, and is this is DC. And when V not equals to 0, the current oscillates with a frequency of, if we write it as Fj, as this. This is AC. This is also we have done earlier, no? This one. Now this third question is consider Josephson junction extending from minus A to A and is modeled by a barrier height V naught. Okay. Minus A to A, barrier height V naught greater than the electron energy E naught. Okay. And the wave functions, both sides are formed by the this wave functions are this 1 equals to root n1 alpha 1. N1 and N2 are the superfluid densities. Okay. Now, and this phi 1 and phi 2, these are superconducting phases. Assume no external magnetic field being present, write down the Schrodinger equation. Apply appropriate boundary conditions, obtain expression for current through the junction in terms of N1 and N2. Okay. So, if we apply the Schrodinger's equation inside this barrier minus A to plus A, and using the barrier conditions also, a boundary conditions also, then the Josephson current that will derive is I equals to IC sin phi 1 minus phi 2. Okay. So this one will be only. Yeah, this one only. This question is basically the repetition of this question number this no question number 3. Yeah, question number 3. Okay, assignment 4 is done then. If you have any question, you can ask or you can leave also. Or just tell me the exam date. If there is no like, other questions, I can leave and I can ask you to leave.
Thank you, ma'am.
Thank you. Okay.
Now leave कर दो.
Okay.
Okay, ma'am.
हेलो। राजी को देखा बोलते हुए न्यूज